Hello, today I'd like to talk about Gauss-Seidel and Jacobi iterative search methods and the associated stopping criteria. So this is a situation where we're actually going to guess what the x's are for the linear system of equations. We need to have a way of saying that those x's are good enough. And we're going to be looking at some floating point error bounds. There's what I call a Griffiths method, and then there's a submultiplicative method. As we do this, we also are going to look at how are the x's changing, and I call that a book polishing bound. So we'll do that, and you might wonder, well, why are we doing this Gauss-Seidel iterative when we can just use an inverse, or we could use Cramer's rule, or we could use Gaussian elimination? Well, Gauss-Seidel works well on large, sparse systems, so that's why we want to have this capability. Don't forget to look at the follow-on numerical example after this theoretical discussion. Okay, so we're going to do iterative method. We're going to iterate on an equation ax equals b. A is a square matrix n by n, and x is an n by 1, a column vector of unknowns, and b would be an n by 1 column vector of knowns. So we're going to be guessing x to see if ax minus b equals 0. We can actually start with Gauss-Seidel. We can actually start with the vector, the array of x's being all zeros, and then kind of start from there. So this notation where we have the parens up top, that's not a superscript. That's actually an iteration sort of marker. So if it's 0, that means that the very first or the 0th iteration, we're starting at x equals 0, for example. And then we're going to update as we carry forward. Iteration k would be based on the previous iteration and also on a and b. So thinking about a 3x3 example, we might denote it this way. So our matrix A would be generically or symbolically represented by these smaller lowercase a coupled with row column indices. So row 1, 2, 3, column 1, 2, 3. And then our unknowns would be denoted by x sub 1, x sub 2, x sub 3. Our right hand would be denoted by b1, b2, b3, and a 3x3 system would look like this. Okay, so this is a Gauss-Seidel and from the book. So how it works is the next x1 is based on the b, the a sub 1, 1, a sub 1, 2, a sub 1, 3, and the b sub 1. And it's based on the x2 of the previous and the x3 of the previous iteration. So that's how you would get the next x1. And then the next x2, you actually would use the just calculated x1 coupled with the previous x3. So the thing with Gauss-Seidel is it's always using the most up-to-date x values that you have. And then for the x3, you're actually going to use the x1 that you've just calculated and the x2 that you've just calculated. So again, Gauss-Seidel always uses the most up-to-date x sub 1, x sub 2, x sub 3. And then, of course, we're relying on the a sub 1, the a sub ij that we have that doesn't change, and the b sub I that doesn't change. If we look at how the book shows it, is that we're using on the left-hand side we've got Gauss-Seidel, so we're always using the most up-to-date x1, x2, x3 on each iteration. The second iteration, we're going to calculate the next x1, the next x2. So that's how Gauss-Seidel is always using the most up-to-date x1, x2, x3. However, Jacobi is going to kind of group them together and is going to use x1, x2, x3 as from the previous iteration. So the second iteration would use x1, x2, x3 in MOS, okay, to get the new x1, x2, x3. So that's the only difference between Gauss-Seidel using the most updated scalar versions of x1, x2, x3, whereas Jacobi is looking at the vectorized x1, x2, x3. Okay, so this is coming from the book, and it's kind of putting this together to where we can look at this in terms of matrices. So our x1, and they're calling it the new, x2 new, x3 new. So x1 new would be based on x2 old, x3 old. And it's kind of spacing it out where you can see very nicely how these things can be presented in terms of matrices. So if you look at it, the x2 new is depending on the x1 new. So yeah, so this is a Gauss-Seidel type of presentation where the x3 is the old or the previous, and then the x3 new is depending on the x1 new and the x2 new, right? So we have this kind of spread out so that you see an x1 column, you see an x2 column, you see an x3 column. It's spreading things out so that you can start to see that you've got a column represented by D, and D is going to be B1, B2, B3 divided by the particular diagonal element. So that's our D, so that's very nicely presented there. And then there's a minus a C matrix, which is going to come from this. Everything is negated, so that makes sense. And then our C is going to be 0 along the diagonal, which you kind of see here. 0 along the diagonal. And then we're picking up A12 divided by A11 there. A13 divided by A11 there. And then we've got an A21 divided by A22 there. And then we have an A23 divided by A22 there. And then we have an A31 divided by A33 there. And then we have an A32 divided by A33 there. I don't think I goofed up any discussion or any subscript there, but very nicely we see a C matrix that is going to be receiving the X values coming through. So this almost works where you're taking the X and multiplying it into the C and subtracting it from a D. So this would actually work for Jacobi. This is, quite frankly, if you were to implement this in software, you couldn't do this for Gauss-Seidel, but it would work for Jacobi. That this would be the X new as an array, and this would be the X old as an array. Okay, so let's see what the code looks like, see if this makes sense. So code-wise, there's some comments up here at the beginning. So this is straight out of the book. And then I'd encourage you to kind of figure out what this whole thing does. But there's some stuff at the beginning which kind of looks at the number of arguments. I'll let you kind of work on that. We'll pick it up right here where we're looking at the size of A, and it's going to give us a number of columns. There's a check to make sure that that the A matrix is square. So that kind of makes sense. I like that. And then it initializes this local variable C to be equal to the A, but then it goes ahead and it, that main diagonal, the CII, as I goes from 1 to n, it's making sure that our C, yea, verily, has zeros along the diagonals, as it should. If you look here, the C, starting it out as A, kind of makes sense because the C is almost A except for zeros along the diagonals, and then we're dividing by certain values as we go. So we could initialize our C to be equal to A, zero out our diagonals, and then divide by the actual diagonal element So that's what C looks like, and it's doing it on a row by row basis right here. So that's looking good. And then we go ahead and figure out our D column as being our B divided by the main diagonal element. So that's how we're setting up here, right? So initializing our X to be 0, and then it's setting it here up to be a column vector where it was a row vector there. So I think that's setting us up. And then here, we're keeping a iteration value. This is, I do, quite frankly, a for loop on this. I don't use a while loop, but it's implementing a similar kind of thing here with using this iter variable as sort of an iteration variable that, if it's going to be over our max IT, which is set to be 50 here by default, then it'll break and end the function. But anyway, so this while loop that they've got kind of set up here is like what I do with a for loop, and it'll set up an old to be the X coming in, and then it'll iterate, and it's doing this iteration for each X sub I. So this is Gauss-Seidel because it's doing it for each row. If you look at how this works, each row and all columns. So this is making sense for a Gauss-Seidel. And then it's doing this book polishing type of check test. That's what I call it. And this 100 is because it's a percentage kind of thing. But I don't deal with percentages. But this is looking at how the individual X's are changing relative to their previous. So I call that the book polishing. And this is the only test that the book actually shows you explicitly. And I look at with you guys, I try to show you what the floating point error looks like, because this is, quite frankly, a little bit arbitrary coming in and setting this E sub S to be that. So I think that's kind of arbitrary. Why would you stop searching when you're getting a better and better answer, right? So that's kind of the theory there. So this is that book polishing, and I wanted to kind of go through and show you the good and the bad of this, and how we can actually make this better. Okay, so here's where I'm kind of going with this is, we want to look at what this AX minus B is doing, and I like to do this in terms of a norm, and we actually will look at a one norm of this, but what does this really mean, how we're doing this? And you're going to get, for a 3x3, you're going to get 3 of these different errors between AX minus B. And, we could think of this, first of all, as just a scalar, just focus on that first row, and say, well, what does that need to be? And, we can think about, well, how's the X1 changing as we sort of iterate through this? So we've done this before when we looked at, maybe the polynomial kind of thing. And this is from our chapter 4. If you remember, we're looking at single scalars here in the chapter 4 type of thing. And we're looking at, how's that floating point calculation of E1 compared to the theoretical E1. We want that theoretical E1 to be 0. That's what we're trying to do, is drive that to be 0. And we're not using the relative error here for the E1. We're going to use the absolute error, and we're going to look at how that, if our E1 is 0, then our calculated floating point calculation, the absolute value of that, we want that to be less than some, and I call it with some round off error, a bound on round off error. Okay, so we do that. And then, we can bring in what the book is doing with that polishing and thinking about how that X1 is changing in a relative sense. Okay, and then we kind of try to put this together, just thinking of bringing back our rooting algorithm here, where our floating point calculation of of our E1 is diminishing, diminishing, diminishing as we look at our iteration. It gets below that we keep going if we can until, well, the xi is not changing anymore, right? So that's kind of how we did it. And we kind of put this back into, now we kind of bring this back into a vector form where we've got the floating point calculation of E1, V2, V3. And, we say, okay, that's going to be a one norm. Quite frankly, you do the one norm of all of those. And, you kind of look at that in terms of the one norm being less than or equal to the one norm of the errs, right? So we do that. And then we kind of put that together with looking at how the x sub i's are changing. And we do a max, we're doing a max of that. So that's the infinity norm of our relative x changes. And then we can bring in that book, the book E sub s. So that's a little bit of an arbitrary bound that the book provides you. But the basic idea is that you're saying that, relatively speaking, the x sub i's are not changing that much. They're less than or equal to some threshold. And that's saying that the x's aren't changing that much and that they are polished is the term I use. The x's are polished. Well, you might as well finish. Okay, so let's go back and take a look at that error, the floating point error bound, is try to set that up, what that really means. Well, the floating point errors, E sub 1, E sub 2, E sub 3, are going to come from the A matrix times x, column vector x, minus the B column. So it sets up like this. So if you kind of focus on just maybe the first row of the first error, the E1, if you will, that's going to come about from three multiplies. You're going to multiply A11 times x1. You're going to multiply A12 times x2. You're going to multiply A13 times x3. So three multiplies. And then you're going to have, we're going to have the sum of the first multiply and the second multiply. You're going to take that sum and you're going to add in the sum of the third multiply, and then you're going to have the final thing you're going to do is subtract the B1. Well, B1 is only involved in that very last thing, so it's only got the one operation. This product here, you're going to have the multiply, plus you're going to have the add to the previous, and then it's going to be involved in that subtraction with B. So there's three operations that this particular term sees, whereas the very first terms, the A11 times x1 and the A12 times x2, they're actually going to see four things. They're going to see their respective multiplies, and then they're going to see the addition to themselves coupled with the addition to the A13, X3, and then the B1. So that's why they see four. So that kind of gives you an idea of where this comes from. And each floating point operation has that epsilon bound that we've been studying. So this is kind of that format that I showed you guys earlier in this semester. So that's going to set my ER1. And you would similarly do that for the E2 and the E3 to set their bounds, respective bounds. And that would give you a column vector of errs. And you could do the one norm of those. And then you could look at that with respect to the actual one norm of the E1, E2, E3 floating point calculations. We could do that. But then I noticed, well, what the heck, I might as well just make that a 4. And it's going to be a little bit bigger kind of threshold. Okay, so if I make that a 4, then I could do a matrix multiply of the absolute value of, take all of that matrix A and go absolute value on everything. And then the X column go absolute value on everything. So this is what I've got right here. Okay, I take the A matrix and go absolute value in all its elements. So that's going to be 3 by 3 in this case. Then I have my X absolute value, so 3 by 1. Go ahead and make that, in this case, a 4. So N is 3. So I just really need to add another value there. So make that a 4 in this case. And then I add in the absolute value of the B. And then I do a 1 norm of that times epsilon. So this is what I call the Griffiths bound. And it's not as tight, and I'm going to slide over here to the left. It's not as tight as the one bound, because we've kind of added in that extra thing there, that extra making that a 4, so we could very easily calculate this. Okay, so that's the Griffiths bound, very easy to calculate. And it's important to understand a couple of things here, the difference between, the 1 norm of the versus what one is, right? So one is a scalar, and it's just one of the scalars. There would be an 2 and an 3, but the vector 1 norm is a 1 norm of the vector, and there's a big difference there between these two things. So the double bars means norm, and the 1 is going to be the sum of the absolute values of everything. And then here, just kind of based on context, you've got to recognize that that's not a determinant. That's actually taking absolute value of all of those elements and still treating it. Here's a 3 by 3, a 3 by 1 in this case, and then that'll be within is 3. That'll be a 4. So 3 by 1, 3 by 3, 3 by 1, and you're going to add in a 3 by 1. And then take the 1 norm subsequently of that. Okay, so big differences there. Okay, so now, so that's the Griffiths method. Now we're kind of thinking about transitioning into that submultiplicative method, which is extremely fascinating to me. But before we do that, I wanted to think about absolute values here. So if you take absolute value of something, absolute value of, in this case, think about a scalar. And if you do that, then the absolute value will always be greater than or equal to 0 for any complex x or real. And it only be equal to 0 if x is equal to 0. The absolute value of a product is going to be equal to the product of the absolute values. And then we use this quite a bit, the triangle inequality that says that if you take two real values and you add them together, the absolute value of that is going to be less than or equal to the sum of the absolute values, the sum of the absolute values. Yep, I said that right. Okay, so that's on absolute value. Now, the interesting thing here is when you transition to a norm. Now, norm is where you take the norm of a vector, and this could be a 1 norm, could be a 2 norm, could be infinity. Whatever it is, once you establish that, then the norm of a vector is going to be greater than or equal to 0 for any vector, complex or real or n-dimensional. Right? And it's only going to be equal to exactly 0 when that x is a 0 vector. If you take a scalar multiple of that vector, it's going to be equal to the absolute value of that scalar times the norm of that vector. Whether the scalar is a complex or real. And then the triangle inequality holds again, and I like that. So if you take two vectors and you add them together, and then take the norm, that's going to be less than or equal to the sum of the individual norms. Okay, so this again works for one norm, 2 norm, or infinity. Okay, so on matrices, this is kind of a big deal. The norm, and we're going to think about a complex n by n, or a real n by n. So on the norms, remember we've got 1 norm, 2 norm, and infinity that I've shown you before. So if we take a norm of a matrix, square matrix, it's always going to be greater than or equal to 0, whether it's complex or real. Would be only equal to 0 when the matrix has all 0 elements. And if I take a scalar times that matrix, well, then that's going to be the absolute value of the scalar times the norm of that matrix. If I take two matrices and add them together, the norm of that is going to be less than or equal to the sum of the norms of the individual matrices. So that's the triangle inequality. Here's a new one. This is interesting. This is called submultiplicativity. And what this says is that the product of the two matrices, norm of the product of the two matrices, is going to be less than or equal to the product of the norms. And this doesn't always hold, but it holds for a one norm, a two norm, and an infinity norm, which we're going to be using the one norm for sure. Okay, so that's the introduction to matrices norms, the laws associated with that, and then the vector norms. Let's put it to use. I just wanted to remind you of the one norm of a matrix. So, and this is an example that we did earlier. So if I happen to have this matrix that looks like this, so the one norm is the max column sum. So if I have 1, 5, 6 as a column, minus 8, 2, minus 4 as a column, 2, 6, 4 as a column, the max column sum is going to be this one. So it's going to be 8 plus 2 is 10 plus 4 is 14. And so that's how we do it. All right, so submultiplicative method. So we're looking at ax minus b, and I want to kind of wave my hands a little bit and say, hey, I want to make that column vector x. I'm going to just repeat that column vector x, right? So if I do that and then create like an n by n, I could do that. The max column sum of that x n by n x matrix will be equal to the one norm of the x. And I'd repeat to do the same thing for b. I would have an n by n b, which is going to be just the b column replicated n times. So the max column sum of the b matrix's one norm is going to be equal to the one norm of the b vector. So you ready for this? Here's what I want to do, is I want to take ax minus b, and the one norm of that in terms of our normal vectors that we've been dealing with, and I want to say that's equal to a times x matrix minus b matrix, the one norm of that. And I want to say that that bound is going to be less than or equal to the submultiplicative a1 norm times the x1 norm plus the b1 norm. So the triangle bringing in the submultiplicativity coupled with the triangle law, and then taking all of that times the machine epsilon, right? And then I know that this is equal to that, so I've got my desired floating point calculation, and I've set a submultiplicative bound in this case. I replace the x matrix 1 with the x vector 1, and I replace the b matrix one norm with the b column or b vector one norm, and I've got the submultiplicative bound established. And this is saying, when this is true, that x is an acceptable solution to the equation ax minus b. Okay, so this is sort of the summary of this. So Gauss-Seidel or Jacobi gives you a way to guess the next x when you're looking for a solution to ax minus b. There are two bounds on floating point errors. There's one that I called the Griffiths method, which is a bound that's related to taking absolute values of the a, the x, and the b, and multiplying the ax product by n plus 1. Then you add in the b vector, absoluted, and then you do the one norm of that, multiply by machine epsilon, and that sets the bound in the Griffiths method. And then the submultiplicative bound is it's actually simpler, quite frankly, to calculate. You do the one norm of the matrix, which is a scalar. You do the one norm of the x, which is a scalar, multiply those two together. You add in the one norm of the b vector, and you take that and multiply by machine epsilon. So there's two bounds on floating point errors. And then, of course, we have our polishing condition that says that the max relative change of any of the x variables is less than or equal to this book stopping criteria, right? So that sets the theory for Gauss-Seidel and Jacobi. So hopefully you've enjoyed that. Don't forget to see the example that I've worked out for you.